All right, this is the last section of chapter 7. So the first part of this is just some history of the periodic table. So if you get a chance, go ahead and read through that in the textbook. They talk about Mendeleev and how he was so important because he was able to predict the properties of undiscovered elements, and he, for the most part, he was right. So he is really famous for that, and they also talk about Moseley and some of the other scientists that contributed to the current periodic table. So go ahead and read through that in the textbook when you get a chance. The next part are some rules that we use for electron configuration and orbital notation. The Aufbau principle, we call this the building up one. This just says that the electrons are going to be as close to the nucleus as possible. So as you're writing the electron configuration, you're always going to build up from the center of the nucleus. So you wouldn't put electrons on the outside of the atom without putting them on the inside first. And you already do this when you do electron configuration, and you even do it when you abbreviate. So when you use the noble gases in brackets, that's still following the Aufbau principle. Hund's rule we talked about the other day. This is the one where you have to spread out the arrows for orbital notation before you come back for seconds, and that's because of the electron repulsion. So for example, if you have a p orbital, p's always get, they always have 3 options for the orbitals, regardless of what number is in front of the p. So even if it's 2p, you're going to have 3 lines. And then as you fill up the arrows, you want to make sure you put 1 in each blank before you come back for seconds. So if you had 4, it would look like that. All right, there's a lot of terms here. Most of these you should be familiar with. Valence electrons are the ones on the outside energy level, and these are the ones that we care about because they give the properties. And that's actually kind of important. Sometimes AP questions will ask about what is the determining factor for chemical properties for something, and a lot of students choose atomic number. And atomic numbers are important. They identify the name of the element, the actual element itself, but they don't talk about the properties of it, or that doesn't determine the properties. So it's the valence electrons that determine like how reactive it is, what kind of things it reacts with, what it does to react. All that, those properties are going to be determined by the valence electrons. Transition metals are in the D block. Lanthanides and actinides are in the F block. Main groups are groups 1A through 8A, and you can see this on the periodic table that's in your textbook. And then metalloids are on the staircase that separate the metals and the nonmetals. So most of that you probably knew from first year chemistry. All right, our very last section for this chapter is about the trends. So first we're going to talk about atomic radius, which is just a fancy way to talk about the size of the atom. And there's kind of a long definition for radius because it's hard to, so first of all, radius is from the center of the circle to the outside. And it's hard to talk about that because there's not really an edge of an atom. Remember we talked about that we plot the probability of where an electron is. So where there's a high probability, it's going to be shaded dark, and then at the edge of the atom, it just kind of fades off into nothing. So there's not really an edge of the atom. It's never actually nothing. There's always some slight chance the electron is there, but it gets really low. But anyway, so it's hard to tell the edge of the atom. So they talk about this definition as being half the distance between radii in bonded atoms that are identical. So if you have 2 hydrogen atoms, for example, what we can do is measure the distance from one nucleus to another nucleus. That's a hard, dense center, so we can get that distance, and then we can cut that in half, and that's how we can get the radius. Really, all you need to know is that when they're talking about comparing the radius of different atoms, really what they're talking about is comparing the size, because the bigger the radius, the bigger the atom is going to be. So for example, the one on the right is going to be a larger radius, but also a larger size. The periodic trend for this is that it's going to increase as you go down because you add energy levels. So as you add rings to they're not all circles, but I'm just drawing like that. Add rings to it, it gets bigger. Remember we talked about the snowman, so you can remember that it gets bigger as you go down. And then it gets smaller as you go to the right. And that one's a little harder for students because if you look at the numbers on the periodic table, they seem to increase as you go left to right. They all, get bigger as you go left to right. So it seems like the atom would get bigger. But really what you're adding is a positive charge to the nucleus. And the more positives you have, the more they're going to pull on the electrons, which kind of shrinks the atom just a little bit. So a couple of things I want to highlight that might be different from first year chemistry. Well, first of all, anytime you're talking about the up and down trend, you want to talk about energy levels. Anytime you talk about the left and right trend, you want to talk about this right here. Effective nuclear charge is a fancy way to talk about adding protons to the nucleus. So it's good if you can go ahead and start speaking like a scientist. Instead of saying there are more rings as you go down, you can say that there are more energy levels. And as you go left to right, instead of saying that you're adding protons, you say that the effective nuclear charge increases. And notice they even talked about shielding as well. So the more you can use these fancy vocab words correctly, the more likely you are to earn points for that AP exam. So as you go left to right, again, it adds protons, which shrinks the atom just a little bit. If you're comparing these two, so if you have to choose between the up and down trend versus the left and right trend, adding energy levels changes the atom more than adding protons. So the up and down trend is going to win in a competition against the left and right trend. They even use the even fancier words, principal quantum levels, that this is the same thing as energy levels. So it increases as you go down and it decreases to the left. I'm sorry, decreases to the right, increases to the left, increases to the left. All right, the next one is the radius of an ion. So as you add or take away electrons, it changes the charge, and that also changes the size of the atom, and that has to do with repulsion of the electrons. So anytime you throw another electron into an atom, it's going to repel against the electrons that are already in that shell, and it's going to push them away and kind of makes it grow so it gets a little bit bigger. So as you get, if you take away electrons and there's not as much electron repulsion, they can get closer to the nucleus. So positive is going to be small and negative is going to be the biggest. We have a few long fancy science vocab words that you actually did in first year chemistry, but you probably need to review. Ionization energy is the energy needed to remove an electron. That's the key idea here. And in first year chemistry, we only did first ionization energies. In fact, we didn't even say first, we just called it ionization energy. But in this class, you're going to start to talk about second and third ionization energies and more. And that just means taking off the second electron or taking off the third electron and that kind of thing. So first of all, let's just review the size of the atom. If we talk about these two atoms, ionization energy is the energy required to pull off the electron. So notice that that first top atom, the electron is right next to the nucleus, so they can really feel that positive charge, and there's nothing blocking the nucleus from the electron. There's not a shielding effect happening there, whereas there is for the second one. So notice that it's pretty far from the nucleus, and there's a whole lot of shielding effect going on, and so this electron is going to come off easier than the top one. And so going back to the definition, it's the energy needed. So basically how much muscle you have to use to pull off the electron. So that first one is going to have a high ionization energy because you have to use a lot of energy to pull it off. Whereas down here, it's going to have a low ionization energy. So ionization energy is partly related to the size of the atom and how many protons it has and the shielding effect and all of that. It also has to do with what it needs to do to become stable. So for example, magnesium, just sketch a periodic table real quick. So magnesium is over here in the second column. And so it needs to lose 2 electrons to become stable. So the first ionization energy, you might see a number. After the second ionization energy, it's going to change a lot because it's going to become stable. So the first and the second ionization energies are going to be pretty low because it kind of, it needs to lose those electrons to become stable. So I always think of it as wanting to lose the electrons. Try not to personify the atoms or the electrons. They don't really want to do anything, but they become more stable when they lose 2. So the ionization energy is going to be pretty low because they need to lose those 2. But then once it becomes similar to a noble gas, so it's going to lose 1 electron and become similar to an alkali metal outside shell. And then as it loses another one, it becomes similar to a noble gas, and then it's stable. And so the third ionization energy would be extremely high because once it becomes stable, it's really going to hold on to those electrons tightly, and it's going to take a lot of energy to remove them. So you kind of have to, a lot of times they'll give you different ionization energies and ask you why is one really high or one really low. And so it's helpful to look at the periodic table and kind of see what's going on to see what's happening to those atoms. In general, as you go left to right, you increase the protons, which is going to mean more of the ionization energy. You have to use more energy to remove it. And as you go from top to bottom, the atom gets bigger. You have more energy levels, so it's easier to pull them off. So in general, ionization energy is going to increase as you go up, and it increases to the right. Oh, in this example, I used calcium, but I was talking about magnesium. They're both alkaline earth metals, so it works for both of them. So the first and second ionization energy for calcium would be pretty low, and then it becomes stable after you take off 2 electrons. So the third ionization energy would be extremely high. This next section is about electron affinity, and we didn't really talk about affinity a whole lot in first year chemistry. It's pretty similar to electronegativity. The difference is that electronegativity is a bonded, between bonded atoms, but both of them have to do with attracting electrons. So if we go back to this picture over here, notice that the electron is going to be a lot more attracted to the smaller atom because there's less shielding effect. It can get right up next to the nucleus. It also could be that there's more protons, which would attract the electron as well. So it's the same kind of idea as ionization energy, except we're talking about the addition of an electron or the attraction of an electron. And sometimes there's some exceptions, and a lot of times on the AP exam, they'll give you the exception and ask why it happens. So this example is talking about nitrogen versus carbon. So nitrogen, if you draw the orbital notation for this, nitrogen is 2p3 is what it ends with. So if we have the 2p and then we put 3 electrons, notice that adding a 4th electron to nitrogen would have some repulsion. So if I add one more, so that green one, there's some repulsion between that green one and the other blue one. And so it's not as likely to happen. Whereas with carbon, for carbon it has, so this was 2p3. Carbon is 2p2, and so carbon has room for another electron. So if carbon is trying to attract an electron, there's space for that extra electron right there. And so there's some exceptions to the rules based on electron repulsion. In general, both of these are going to increase up and to the right. So they increase as you move up and increase to the right. And that's because as the atoms get smaller, they're more likely to attract electrons. And that's moving up. And then moving to the right is the increase in the effective nuclear charge, which is going to attract electrons as well. However, you do have to be careful. There's some exceptions here that you need to exclude the noble gases. And we did talk about that in first year chemistry. So for electronegativity, noble gases are way over here on the right. They are never going to try to attract electrons regardless of their size because they're already stable. So helium is not the most electronegative, even though it's in the top right corner. Fluorine is actually the most electronegative element. And that goes for the that goes for electron affinity too, but not the ionization energy. And there's some properties that you can read through. The textbook goes into even more detail if you're interested. And just a couple more things. I already mentioned this, but the vertical trends are more significant than the horizontal trends. So again, if you have to choose between the vertical or the horizontal trend, adding energy levels changes the atom more than adding protons or changing the effective nuclear charge. And be careful with fluorine. You'll notice that it's an exception to a lot of rules, and that has to do with its size, that it's just so small that the electron repulsion becomes more significant. So just be careful with fluorine. And that is it for Chapter 7.